Here is a diagram of a conventional fossil fuel steam turbine generator. A conventional fossil fuel steam turbine generator produces electricity by burning a fossil fuel to boil water, to produce high-pressure steam, to rotate a turbine, to power a generator, to produce electricity. By contrast, a vapor turbine generator produces electricity by using solar power alone to vaporize an alternate working fluid with a lower boiling point, to produce high-pressure vapor, to rotate a turbine, to power a generator, to produce electricity within a closed, sealed system. The working fluid is completely recycled. No user-supplied fuel is needed or used, and there are no pollutants, greenhouse gases, exhaust, noise, or fuel cost. It may be installed in a house. It will work in a backyard, an attic space, a Prius or Tesla, the desert, or on the moon. Here's a comparison showing two ways to generate power: a conventional fossil fuel steam turbine generator and a vapor turbine generator. As you'll see, they have much in common, but significant differences. Here's a detailed explanation of some of the major differences. Here is another explanation and diagram of a conventional steam turbine generator showing the burning of fossil fuel, heating water, producing steam, rotating turbine blades, powering a generator. And here's another explanation of a steam turbine generator, which is mostly what we use today. I would call attention to a few critical words. A steam turbine generator burns a fossil fuel to produce electricity. The spent steam is sometimes cooled, condensed, and recycled. Here's the same process in even fewer words. For a conventional steam turbine generator, the working fluid is water, which boils or vaporizes at 212 degrees Fahrenheit at normal atmospheric pressure at sea level. This high temperature is not commonly found in nature. Here is a list of lower boiling points of some other compounds. Butane, isopentane, ethanol, and isopropyl alcohol are of special interest. On a cool winter day in central South Carolina, the thermometer in the sun shows 56 degrees Fahrenheit, but it was colder in the shade. The small, flat black, non-reflective toolbox is a nice 98.2 degrees Fahrenheit. 98.2 degrees Fahrenheit is more than enough to boil butane or isopentane. The 82 degrees Fahrenheit needed to boil isopentane is found right outside my house in South Carolina for months at a time. And my attic is much warmer than that for days at a time during the long hot summer. Attic temperatures of 150 degrees Fahrenheit or higher midday are common. Please recall, a steam turbine generator burns fossil fuel to produce electricity. Here's an illustration. Ambient temperatures are in the 90s Fahrenheit. The attic is 150 degrees Fahrenheit. The soil temperature 10 feet underground is 55 degrees pretty much year-round. We put a heat exchanger or radiator in the attic, connected in an endless conduit loop to another heat exchanger buried in the ground. That's a heat exchanger or radiator in the attic, connected in an endless loop to another heat exchanger or radiator buried in the ground. We add a one-way check valve and a pressure relief valve to the fluid circuit. We add a fluid turbine and generator downstream from the pressure relief valve. The entire loop and both thermal exchangers radiators are filled with isopentane, which vaporizes or boils at 82 degrees Fahrenheit. The upper radiator absorbs 150-degree attic heat. The isopentane within tries to expand, but it is trapped in the upper radiator between the one-way check valve and the pressure relief valve. The pressure within builds. At a set point, the pressure relief valve pops open. The hot, pressurized liquid isopentane comes charging out of the upper radiator. It immediately vaporizes because it is above its boiling point and the pressure has been quickly reduced. The hot, pressurized isopentane vapor powers the fluid turbine, which powers the electrical generator. The hot, low-pressure isopentane vapor is forced down the red conduit into the lower heat exchanger or radiator where it cools and condenses, and the cycle repeats. Winter temperatures and overnight lows in Boston are often well below 31 degrees Fahrenheit for months at a time, but the temperature of flat, black panels placed in the sun easily exceeds 31 degrees during much of the day. This is enough to vaporize or boil butane. Here's a black Corvette parked in the full sun, 92 degrees in the shade, but 185.3 on the roof of the car. This is very close to the boiling point of water. How much pressure could be produced? This is a 1-foot long piece of 1-inch diameter black iron pipe filled with 1 cup of olive oil. The ambient temperature was in the low 90s Fahrenheit. The result was 1,800 psi, pounds per square inch, of hydraulic pressure, at which point it sprang a pinhole leak at one of the joints, probably just prior to exploding. I must note this is dangerous. Do not attempt this on your own. With ambient temperature in the low 90s, the top of the black car hit 185.3 degrees Fahrenheit when parked in the sun. This is more than needed to boil ethanol at 173 degrees or isopropyl alcohol at 177 degrees, which can cool and condense in the shade under the car. It will not be that hot under the car. This innovation is protected by a U.S. patent shown above. Power generating system utilizing expanding fluid allowed to me on February the 9th, 2021. For more information, please contact John at lookforthepower.com. Thank you.